We've had a few lectures in a row now talking about the best way to encode individual symbols independently. So once we have some idea of what our symbols are, and we know their expected frequency, or we know their information content, we can come up with encodings that fairly value those symbols. And we're not actually done talking about that subject, about entropy coding, but we know enough for now to make some progress towards talking about a real scheme. And the real scheme I want to talk about really soon, which is to say in the next lecture, is deflate. We need one more thing before we can talk about deflate, and that's some knowledge of the other machinery deflate uses before it uses entropy coding, before it generates a prefix code. And in the service of doing that, we're going to talk today about Lempel-Ziv schemes. And Lempel-Ziv schemes are one way of addressing the problem of seeing an input sequence that contains patterns across multiple symbols, so dependencies in the data. So for example, we've already actually seen one Lempel-Ziv scheme, LZW. For example, we could observe that this subsequence, AABC, has already occurred in my input. And so maybe instead of transmitting the characters AABC a second time, I could just tell my decompressor, hey, could you just go back a few characters and photocopy those characters you already generated? And maybe, if I'm lucky, that can save me some space. So we've already seen LZW, and we'll notice a common theme forming here, which is that all of our Lempel-Ziv family, our LZ family of schemes, including LZW, tend to contain L and Z in their name. That doesn't usually mean that Lempel and Ziv directly authored the scheme in question. So LZW, as I mentioned in Lecture 3, was authored by Welch, but it was based on previous work by Lempel and Ziv, and it was so based on that work that it's reasonable to give Lempel and Ziv credit. And so LZW is a member of this broader family of Lempel-Ziv schemes, all of which trace back to one scheme that is now called LZ77 because it was published in 1977. And I've drawn here a sort of abridged, very abridged, family tree of the Lempel-Ziv family. So because this course is chronically short on lecture time, because I really would like to cover every single topic in the universe, but don't have time to do that in only a 3-month course, I'm only going to cover a very small subset of Lempel-Ziv schemes, enough to give us this scheme here, which we're going to need to talk about deflate, and enough context, so we should know about the original scheme LZ77, and maybe a few other members of the family just to get an idea about the differences one tends to encounter within the family. But there is actually a huge family of Lempel-Ziv schemes, including a lot that are probably a bit out of date by now or aren't really used that much anymore, but were at one point significant, and quite a few that are still very significant. In fact, if you were to take a look at the Handbook of Data Compression, which is one of our books in this course, you will find that there are section headings for no fewer than 16 different Lempel-Ziv schemes. And I would argue if there are 16 appearing in that book, there are probably a whole bunch more out there in the world that don't really deserve that level of documentation. But we don't have time for that, and actually, given that this course is supposed to be an overview, maybe we don't need that level of detail for all 16 or whatever number of members of the family. So mainly today, I want to get us to talking about this. And we're going to notice that all of the Lempel-Ziv family pretty much inherits a lot from LZ77. And many of the disagreements that occurred later in the family tree come down to questions about how to encode the fundamental insights that LZ77 provides. I'm going to talk a little bit later as well. The one fork I've created in the family tree here, because there are a variety of different Lempel-Ziv schemes in the family and different branches of the tree, this particular fork I think is very significant. There's a certain schism that exists between these two branches of the family, and I'll unpack that a little bit in a few slides. So as you recall, LZW down on this branch is used by things like this image format from the 1980s, as well as the ancient Unix compress tool, also from the 1980s. So LZW is a pretty big deal when it was invented. I also mentioned around lectures 3 and 4 that when there became this problem with patents with LZW and many of the schemes, many of the compression tools using LZW suddenly became a bit of a liability, it was around that time or just after that time that deflate caught on. So deflate was able to benefit from the sort of vacuum that was left by LZW. And deflate didn't use LZW or any of LZW's progenitors except for LZ77. One reason was because both LZW and LZ78 were affected by patent issues. But it turns out that deflate was a pretty good scheme, and that even once the encumbrance of the patents was resolved, LZW couldn't really compete with it, and that's one of the reasons that LZW isn't used that much today. And I think, as far as which branch of the family tree ended up winning, I think by today's standards, probably this one. So schemes like deflate, which of course is ubiquitous, but also LZMA. Now it turns out that the MA in LZMA isn't really related to which variant of the LZ family is used, but it turns out LZMA, I think, by modern standards, would be considered to be a descendant of LZSS. There's a bit of confusion about that. Schemes that are based on LZSS often claim to just descend from LZ77 directly. I don't take that view, and I think I can justify why that is when the time comes. Also, I'll talk about that a little bit more in the lecture on deflate. So LZSS is used by deflate, which of course is going to be a big deal for us. Recall that deflate is the basis of gzip as well as zip archives. It's worth noting that deflate was actually invented for the sake of zip files. And later it was the fundamental logic of the scheme was sort of extracted and used to create the gzip tool, which I now associate deflate with, although it turns out it was invented for zip files. Deflate is also used embedded inside a lot of other formats, including PNG images, but also including a lot of formats that you probably use regularly. So, for example, because of deflate's use in zip files, if you ever see a file like .docx, that actually is a zip file in disguise, and therefore it uses deflate, or it has deflate available as an option. So the basic insight introduced in the LZ77 paper, so I think the one thing that all of the members of the family have in common, in one form or another, was the idea of something called a back reference. And that is the idea that if you're sitting inside of a sequence of text or other data, it's pretty likely that over time, in real data, you're going to see the same subsequence over and over again. So for example, here we see the sequence BCD, even though it just occurred a few characters ago. So perhaps we can save some bandwidth by having by sending to the decompressor just instructions to duplicate some previous characters, rather than sending the characters B, C, and D. Another important concept of LZ schemes is something called a sliding window, which is, I guess, sort of a practical constraint. It's a way of constraining what a back reference can mean in the service of actually having a scheme that can be implemented practically. So the basic idea behind LZ schemes is this assumption that we're going to see repeating subsequences of data somewhere in our input, and that ideally we could condense them down into some form that saves bandwidth. And so you'll notice in these slides, I like using this sort of tableau for LZ77-based schemes. For one branch of the family tree, I like using this tableau because an encoder that is encoding for LZ77 or its descendants will typically know a certain amount about future characters. So an encoder might read forward 6 characters into the future. The idea being that way it can see any patterns forming in the upcoming data that it could take advantage of in previous data. For example, this. An encoder will also keep track of a certain number of previous characters. For the sake of making that clear on the slides, I've decided to adopt a sort of uniform numbering scheme where the character I am about to encode will be at index 0. So think of that as being the current time. Time equals 0. Time equals 1, so one character in the future is a future character, so positive numbers go forward into the future, and negative indices go back into the past. If I find a pattern that has previously occurred, so if I notice when I'm staring at character 0 and I can see a little ways into the future, if I notice that a particular sequence is something I've already seen, what I can do is emit a back reference. Instead of actually printing out the characters B, C, and D, I can give the decompressor instructions to recover that information from characters it's already decoded. And we know from lectures 3 and 4 that one of the clever tricks used by LZW is this idea that the decompressor can use its knowledge of previously decompressed characters instead of having to send extra overhead explaining what you, the compressor, are about to do. So we know that the decompressor would have access to a certain window of previously encoded characters or previously decoded characters, and we can leverage that. We can tell, for example, tell the decompressor, when I get to these 3 characters, instead of just sending over B, C, and D, I can give the decompressor instructions, go back by 4 characters from the present time, and then duplicate the next 3 characters. And we call that set of instructions a back reference. And I'm going to represent it in these slides by this notation with a colon. In this set of slides, because I think it's more natural to talk about how far back and then how long in that order, I'm going to have the distance to go back into the past be first, and then the length of the duplicated string to be second. I am actually going to switch notation in the next lecture. So I'll give you a warning about that. I know that's not really good form to do that, but I actually really do feel like it makes more intuitive sense to talk about back references with distance backwards first and then the length of the back reference second. Now, the problem with this is if we're decoding huge amounts of data or if we're compressing huge amounts of data, so if I have fed the compressor a terabyte of data, well, obviously, yes, it's possible that the sequence BCD or even BCDFGH has occurred somewhere in the distant past. But I can't expect the compressor or the decompressor to remember literally every character that they've seen so far, because that would violate our streaming requirement from back in lecture 2, but it would also create serious practical headaches like memory consumption problems. There is going to be a limit to how many characters a compressor and decompressor can remember. We also have this other problem, which is that when I'm compressing my data, I don't actually know that much about the decompressor. I could compress my data now and decompress it in 10 years on a different machine. So we have to establish some kind of standard of how far back a back reference can go, because it can't go all the way back to the beginning of my input, because my input could be incredibly long. So instead, LZ schemes have a predefined sliding window. When I design my compressor and decompressor, I define a limit to the window of previous characters I'm supposed to remember. And we call it a sliding window because as I move along in my input, characters that are old move out of my window and characters that I've just encoded move into my window. So in a sense, it is a sliding window. And we have to make sure if we design a scheme, an LZ-style scheme, to keep that sliding window size consistent between compressor and decompressor, because obviously if I generate a back reference that's outside of the decompressor's context, how is it going to deal with that? And notice that, of course, by limiting the size of my sliding window, I limit the opportunities to produce back references. So here in this input, I've got the sequence BCD again. Actually, I also have FGH occurring later. But notice that with a sliding window of size 6, I'm not able to generate a back reference and recover this previous occurrence of BCD. It's too far back. And that's fair enough. We're going to see issues like that showing up every time we introduce a limit. One thing I'll observe as far as these slides are concerned is, for the sake of illustration, I have to be able to fit my entire window on the slide, and that means I have to choose extremely small window sizes. In practice, a sliding window would probably be way, way longer than this. So Deflate, for example, uses a sliding window of size 32,000 or 32,768. So in these slides, if you notice that the LZ schemes do not seem to be performing very well, remember that might just be because I've chosen a very small sliding window size. And so in this case, remember that although this is a recurring subsequence, its previous occurrence was so far back that I'm not allowed to benefit from a back reference at this point. So one other feature of LZ schemes that I'm going to talk about a little bit more later, I'll explain why this is so helpful later, but I want to bring it up now, is that the only real requirement of a back reference, so if I'm currently encoding this character here, this is t equals 0, this is the current character, the only real requirements of a back reference are that I don't go further back into the past than I have, so I'm not allowed to go any further than character -8, although of course in this case I can't even go further than character -3 because there aren't any other characters in the buffer. I can't go back further than 8 characters if I have a window of size 8, but I also, of course, can't attempt to make a back reference that points into the future, because how would the decompressor understand go forward by 5 characters? The decompressor doesn't have any future characters. But as long as I go at least 1 character into the past, the back reference is valid. And that applies even if the back reference overlaps the future. I must start my back reference in the past, but I don't have to finish my back reference in the past. So in this sequence, notice how I have generated this peculiar back reference that says go back in time by 2 characters and then generate 6 characters. And if we're the compressor, so we have access to all of the future, to a certain number of future characters, we hopefully can see why this is beneficial. Because notice how I see the sequence BC occurring over and over and over again, and I could benefit if I can step a little bit into the future with condensing down all of those BCs into one long run of characters. So this back reference appears to be a bit of a contradiction. Go back in time by 2 and then walk forward by 6. But it is valid, and I want to illustrate how the decompressor can still recover this. What it comes down to is something that might ring a bell from lecture number 3, which is as long as the decompressor can stay just 1 step ahead, everything is going to be fine. So suppose the decompressor has hit this point. So the decompressor sees the back reference, and it's trying to decompress this character here. It just finished decompressing the C. Okay, so the back reference says go back in time by 2 and then keep running through previous characters until you've generated 6 of them. Okay, so can I do this? Well, the back reference appears to encapsulate 6 characters starting here. I don't have some of those characters, so it's going to be a bit of a tall order. But can I make just a little bit of progress? And I think I can. So let's see, go back in time by 2. Well, if I go back in time by 2, then I get the letter B. Okay, so I now have 1 of the 6 characters I'm supposed to generate. Okay, can I generate a second one? Well, the second one would be go back in time by 2 from here and then step ahead by 1. Well, that's this character, and I have that, so I generate the character C. And when I'm trying to decode this character, it'll be go back in time by 2. Well, I have that too. It's also a B. And maybe you can see what's happening here. It's that as long as I had some way of starting my back reference, I can sort of bootstrap myself into having all of the characters that I need. Because as I generate characters, they enter my sliding window, and I can use them to generate the result. And so the slides are going to walk through this. And so as I walk forwards, as I parse my back reference and generate characters, it increases the context that I have available, and over time, I am actually able to generate all 6 characters of that back reference. So although it's odd that my back reference overlaps into the future, I am able to recover all of the characters. And if you stare at this for a minute, you might realize this is rather familiar because although LZW works a little bit differently than this raw back reference representation, this sounds a lot like the CSCSC problem from Lecture 3, and it turns out it is. So in LZW, when we see the CSCSC problem, we're just seeing a back reference through a few layers of abstraction, a back reference that overlaps the future. And as long as we can recover just a bit of what that back reference refers to, we're going to be fine. So this is actually a really cool feature of LZ schemes, and I'll bring it back up later in this lecture to talk about one thing it does that really helps us out as far as reducing the complexity of our compression scheme. In the meantime, I want to talk about LZ77. So we know what a back reference is. We understand this idea that we set our sliding window to have some fixed size, fixed in advance. Now it's also, I guess, possible that if you're designing a compression tool, you could have the sliding window change in size as long as you tell the decompressor when to make the change. But for our purposes, we'll assume that the size has been agreed upon in advance. So as I mentioned a few minutes ago, the big differences you're likely to see among members of the LZ family are mostly to do with how we encode the data. So they all use back references in some form or another, and a sliding window of some form or another. The real differences tend to be how do we encode that into a bit stream. And we'll notice the early LZ schemes, so LZ77 and LZ78, have pretty clunky encodings. They're mostly demonstrations of the results you can achieve with back references, as opposed to actual examples of bit streams that give you good compression. One other thing I'm going to illustrate is the schism I mentioned earlier between this side of the family over here and this side over here. A schism that was sort of created by Lempel-Ziv because LZ78, the first thing on this branch of the family tree, was a paper authored by Lempel-Ziv. And this branch of the tree is the branch that likes to use symbol tables, as we know from LZW, whereas this branch of the tree over here likes to represent back references explicitly. So it represents them just as distance and length. So I'm going to begin by talking about LZ77. And one observation I want to make right off the bat is that data compression tools, the things that we use today to achieve compression, so a compressor for PNG images, or the gzip tool, or whatever, or even the ancient Unix compress tool, those didn't really exist in the same way they exist now, or in the mid-80s, back when the original LZ77 scheme was invented. Certainly data compression was being studied at that time, and there were programs that could perform compression, but people studying data compression and authoring papers about data compression weren't necessarily as preoccupied with things like show me the bit stream. Instead, they were preoccupied with more theoretical questions like what techniques tend to result in compression in the long term. As I compress an indefinite amount of data and that amount gets larger and larger, what techniques are likely to produce good compression, likely to save me space? How I encode that into bits might be somebody else's problem, especially in these I guess the days of these primitive compression schemes before we even had the ancient Unix compress tool. And as I've mentioned in previous lectures, there were compress tools before this program, but they weren't as widespread and they weren't as generally useful. So this means that if you notice that LZ77 seems a bit clunky, that's because Lempel-Ziv's intention wasn't really to design a tool that could save you bits on a 500 kilobyte file, which is what the Unix compress tool was designed to do, because that was back in the days at the dawn of personal computing in the mid-1980s, when people might not have a hard drive at all, and if they had a hard drive, it might have a capacity of like 5 megabytes or something. So back then, it was pretty important that if you wanted to compress data, you could compress a 50 kilobyte file down to, I don't know, 30 kilobytes or something. Whereas a designer of a scheme today wouldn't care so much about tiny files, I guess, but also a designer of a theoretical compression scheme in the 1970s would be thinking about the big picture issues of how do I get compression in general, not how do I reduce the size of small files to be a little bit smaller. So that means we shouldn't hold it against Lempel-Ziv if LZ77 isn't so impressive from a modern bitstream-centric standpoint. The idea behind LZ77 was to partition your input sequence into a strictly alternating sequence of backreferences, which I'll just denote by B's, and literals, L's. And the idea was you must always follow a backreference by a literal, and you must always follow a literal by a backreference. You are allowed to generate empty backreferences, because there could be places in your sequence where you can't refer back to anything. So for example, if I look at a sequence like A, B, A, let's do one more, A, B, A, C. Well, if I want to generate the very first character, it has to be a backreference, but I don't have a backreference here. There's no history. This is the very first thing. I'm at the dawn of time. So what I could do here is, as my first backreference, I could generate an empty string. Well, that's a bit of a waste of space. Like I said a minute ago, Lempel-Ziv's intention wasn't to design a real tool. It was to prove a point. Okay, so my first backreference is empty. Well, then my literal is going to be the letter B. Or wait, the letter A. Sorry, I'm getting one step ahead of myself. My literal is now the letter A. Okay, so what do I do with the letter B? Well, I have to generate a backreference, and I'm standing on the letter B. Well, okay, there is a history. I'm no longer at the dawn of time, but the only thing in the past is the letter A. So I can't generate a backreference, so again, I generate an empty backreference. Okay, and now my literal is the letter B. Okay, so I move on. Now I'm at the letter A again. Well, okay, in this case, I can generate a backreference. If I walk backwards by 2 steps, I hit the letter A again. So my backreference can be go back by 2 and forwards by 1. And then my literal can be the letter C. So in the original LZ77 conception, the idea was you always alternate backreference and literal. And if there are cases where that's impossible, then you make your backreference empty. And then you just set the literal to be whatever the next character is. One of the, I guess, insights behind this, one of the reasons why we think alternating backreferences and literals makes sense in the long run, I mean, because even the authors would have known that at the beginning of your sequence, backreferences are going to probably be empty. One of the reasons that it makes sense to alternate backreferences and literals is if you're taking a look at a sequence that's a bit longer. Let's do this one here. Notice how ABA appears twice, both at the very beginning and then later on. So that means when I finally get to this, ideally I can generate a backreference of length at maybe 3, maybe 2, depending on how things break down. But why can't I generate a longer backreference? That's, I think, the insight we should think about here. So why can't I make this backreference longer than 3 characters? Well, it's because there's this D in the way. I don't have any other use for this D because I've never seen a D before, so there's no way I'm ever going to get a backreference if I've never seen a D before. And that means if you're thinking about why can't I make my backreference longer, the limiting factor will always be there's a pesky literal at the end of this sequence that gets in the way. So I guess it makes sense. I want to generate the longest backreference I can, followed by just omitting whatever literal got in my way. If this D is what's standing between me and a longer backreference, let's just omit it as a literal just to get it out of the stream so I can begin working on longer backreferences. And I guess conversely, if we think about it from the point of view of why am I not omitting a shorter backreference, okay, so suppose I, for some reason, wanted to omit this backreference here, just AB. Well, the next literal fits very neatly into the same backreference, so why wouldn't I make the backreference longer? So it makes sense that having a backreference followed by a literal sort of pushes you towards making your backreference as long as possible and only generating that literal when you've got something that just can't be folded into the backreference. So I think that's the basic intuition behind this pairing up of backreferences and literals. However, we'll notice that later entries of the family pretty much do away with this immediately. So a lot of the improvements, LZW and LZSS get rid of this idea of pairing up back references and literals, because in practice, for real compression schemes, it doesn't make very much sense. One of the reasons it might make sense in theory is that if you always partition, if you always pair things up, you can then consider the entire stream as being a set of back reference literal pairs, where you always know you're going to have a back reference, then a literal, then a back reference, then a literal. Another reason why this is sort of helpful is if you are decompressing this stream, you don't need any logic to know whether the next thing is a back reference or a literal, because there's a strict one-to-one alternation. Okay, so I'm going to come back to all of those points in a few minutes. In the meantime, let's take a look at LZ77 itself. So because back references are actually pairs of things, this idea of encoding pairs of back reference comma literal, really what I end up doing is creating triples, where I've got the back reference in two parts, distance and length, followed by the literal. So it's actually a triple, not a pair, but it represents a back reference literal pair. All right, let's try encoding this sequence. I'm going to use a window size of 6 characters, so I can see 6 previous characters in my sliding window. So I'll start by encoding the letter A. And we can observe that, of course, I can't generate a back reference because there is nothing in the past. I am at the dawn of time. So I emit this back reference. If I emit a distance of 0, hopefully the decompressor gets that I have nothing, there is no back reference, and the length of 0 should really drive that point home. So 0, 0 is a trivial back reference that does not generate any text at all. It is just the empty string. Okay. I do the same thing for the space character. I have no choice. There are no previous space characters, and I have to generate a back reference followed by a literal. And I'm going to do this for a little while. Eventually, when I get to the second occurrence of A, well, I can copy one A from the previous bytes of input. So I can use the back reference part of my pair to refer to the A, and then the literal can become the S. So now at least I'm taking advantage of all of the parts of the pair, even though here, maybe you can already see, as a compression expert, you can see the extra machinery needed to represent these pairs probably is going to eat up a lot of space that I could otherwise be saving. Okay, same story with the next thing. So the S, I can just duplicate the S from a minute ago. I can just go back in time by 1 and recycle that literal. And then the semicolon becomes the literal part of the next pair. Same thing with the space. So I can store the A as a literal, and then the space, I can just go back in time and grab that space from earlier. And then same thing here. So I get some benefits of back references, but notice that so far all of my back references have length 1. And if my back reference has length 1, what I am encoding is a single character. So why not just encode the character as a literal? That's the question that comes to mind for me when I stare at this scheme. If I have a back reference of length 1, I'm not really getting any of the benefits of a back reference. And I think that's borne out in practice. For very small window sizes, we'll actually notice that it turns out a back reference of length 1 can sometimes be strangely helpful. And so because of the window size, if you're noticing this is sort of underwhelming, part of it is due to the window size, because this substring here, semicolon space A space, well, that actually did occur earlier. So I'm sitting at this point in my sequence. Earlier, I did see semicolon space A space. The problem is the beginning of that substring has already exited the sliding window, so I can't reuse it. So I'm forced here to generate a literal. I actually have no semicolons in my history, so I have to generate a trivial back reference and a literal as a triple to itself. If my sliding window were 1 character longer, I probably would be able to do something with this, but bad luck. I'm using too short of a window. All right, so I keep walking along, and we can see here I'm not really getting any benefit. Finally, near the end, as I'm generating ALAS, it just happens that I have ALA still sitting in my window. And so I am now finally able to generate a back reference that actually looks sort of interesting. Go back by 6, go forward by 3. So I'm now packaging up all 3 of these characters into this one back reference. Here, I suppose I am achieving undisputed compression. It's possible maybe I can encode these triples with a short back reference in a very compact way, but it's hard to really agree that that's going to produce compression in most cases. Here, I could argue I am definitely condensing several characters down, but it took quite a while to do that. All right, and then finally when I get to the end, well, if I'm sitting on this last character A, what do? I have to generate back reference literal. So one option is to generate a back reference for the A, and then to have a special marker to indicate that the stream is over. So a special null literal or end of block marker. We'll notice that deflate uses end of block markers, although deflate does not do this whole triple business. Alternatively, I could just generate a trivial back reference followed by the literal A. If I have an odd number of characters, or if I'm left over with only 1 character, I can't generate a non-trivial back reference followed by a literal because there aren't enough characters left. I've got a few options there. So either this trick, the end of block marker, or this trick. Hopefully, if you're staring at this, as I've been harping on about for the last few slides, the encoding apparently used by LZ77 seems a bit bulky. This 30 character input was transformed into 18 of these triples. And using the window size I've chosen, which is a window of 6 characters of history, which means distance will be a number between 1 and 6, so I guess I need 3 bits to represent distance. My length can be, I guess I could go back 6 characters, then I could go forward by as many as 12, so I need 4 bits for the length, and then the literal, I guess, has to be 8 bits long. That means that each of my triples requires 15 bits to store, so I need 270 bits to represent this, compared to my original sequence, which was 30 characters, each of which is 8 bits, which requires 240 bits in total. So that's 270 is greater than 240, so I'm not getting compression here. But hey, maybe it's because the sequence was too short. Maybe if I had a longer sequence, or a sequence with more patterns, or whatever, I would argue that yes, there are probably some obvious, maybe low-hanging fruit here that I could adjust, some things I could change that would make my scheme a bit more efficient. And I should add, part of that's the window size. So actually, if I choose to encode my triples with a 3-bit distance, then why don't I just have 8 characters in my sliding window? If I use a 3-bit distance and distances start at 1, then there are 8. I can go up to 8 into the past. So why don't I just have a window of length 8? That probably would improve things. And a 4-bit length, similarly, why don't I look forward into the future by 8 characters, allowing lengths to be up to 16? If I'm using a fixed width binary encoding, why don't I saturate the possible values I can use? So if I were to use a longer window, which doesn't fit on the slides as well, at least for an in-person lecture, this might get too small, then I will observe that I can get, notice that semicolon space a space, I'm actually able to capture that from the past. So as usual, if you make the window longer, you probably get better back references. And here I'm actually managing to condense down 4 characters into 1. And if I go all the way to the end, I am also able to get, I'm able to achieve a few multi-character back references. And so in this case, instead of 240 bits, I'm still using 15 bits per triple, so I'm now down to 225. Okay, so LZ77, even with the bulky encoding, does give us some compression. But as compression people, we can stare at this and maybe observe a few places where some improvement would not only be needed, but also be pretty easy. And for me, it's these. All of these back references that are trivial seem to be wasting tons and tons of space. Generating the empty string, but requiring 7 bits to do it, because remember that the back reference here requires a total of 7 bits, 3 bits for distance, 4 bits for length. Needing to spend 7 bits telling the decompressor to do nothing seems like a huge waste of space. I'm also a little bit concerned about short back references. Now it turns out in this case, strangely, a short back reference is only 7 bits, which means a back reference of length 1 is actually more efficient to encode than a literal, because a literal is 8 bits. But I realize that if I want a larger sliding window, well, the larger the sliding window is, the more bits I need for distance. And I would argue that 7 bits is probably not likely to be seen in practice as far as a back reference size, because odds are our sliding windows are going to be massive. If our sliding window has 32,000 previous characters, if it has size 32K, then I'm going to need 15 bits. That means in general, back references are going to take up a lot of space. So I want to make sure I'm not emitting back references unless I'm actually saving space in doing so. So if I use a window like gzip does of 32,000 characters, back references are going to be pretty large. Although in gzip's case, as we'll see in the next lecture, it's a little bit more complicated than just saying, oh, a back reference is 15 bits or something like that, or 16 bits or 32 bits or whatever, because gzip takes all the back references and puts them into a prefix code. It actually generates prefix encodings of back references in a way that, well, you'll see. Just wait for the next lecture and you'll see. So I think this triple-based encoding is inefficient. Now, the idea of having triples isn't inherently the problem here. It's the constraint that we require every literal to be coupled to a back reference and vice versa. If I notice that there are places where I could generate 2 back references in a row, I'm not allowed to do that here because I have to have every back reference, every pair of back references must be separated by a literal. Similarly, if I notice a bunch of literals in a row, so A space L at the beginning, I have no choice but to generate a bunch of meaningless back references because of this forced pairing of back reference and literal. So to me, that seems like an easy thing to fix. And so, an improvement is a scheme called LZSS. One thing to observe, as I said at the very beginning about LZ schemes, is that we'll often see the names, the letters LZ in the name of the scheme. To be clear, this LZSS scheme was invented by these two. It was published in a paper authored by just these two authors. However, it built so much on the original LZ77 scheme that of course we should give credit to Lempel-Ziv for its invention. We shouldn't just call it the SS scheme because S and S owed a lot to Lempel-Ziv in their construction. But to be clear, Lempel-Ziv did not author this scheme themselves. This was an improvement on their work. The idea behind the LZSS scheme, I think the fundamental idea, was we don't need to pair up back references and literals. Instead, let's just have two different types of symbol. You can omit a literal if you want, you can omit a back reference if you want, and you can choose how to interleave them. You can have a bunch of literals in a row, you can have a bunch of back references in a row, you can choose to pair them up, it's your business. And they did this by just having a 1-bit flag. So the beginning of each symbol will be a 0 or 1. And for example, we could choose if the first bit is a 0, we'll call this bit the flag bit, then the next 8 bits will be a literal. So if the flag bit is 0, then it'll be followed by an 8-bit literal. Notice that by doing this, literals are now going to be 9 bits, which is a problem, but we've learned in the past that there are times where increasing the number of bits can help you. If our flag is 1, then we will follow it by a back reference. Now, if we continue using a 6-character sliding window and 6 characters of look ahead, then I guess our back reference is going to be 7 bits. So I'll say this is going to be a 7-bit back reference. And notice that just like in the previous example, back references are therefore more efficient than literals. So if you can find a back reference of length 1, it is better to generate a back reference than to generate a literal. That's only because of the small window. If my window size were smaller, if my window size were larger, then of course back references would require more bits. And in general, in practice, the window size is very large because the larger of a window you have, the more likely you can find long back references. And of course, a long back reference will always be more efficient to encode with a sufficient length than a bunch of literals. So in this case, because I have a case of back references, each back reference requires a total of only 8 bits versus a literal, which requires 9 bits. In this case, it is still beneficial to encode back references instead of literals, even back references of length 1, because of the small window size. So the result of LZSS, I guess conceptually, looks sort of like this, keeping in mind that when you encode this into bits, you'd have to add a flag before each symbol to tell the decompressor, am I looking at a literal, am I looking at a back reference? And so in this case, with a small window size, these tiny back references, I don't know if I call 1-character back references trivial, but in this example they would be, because you'd never generate a 0-character back reference. It is still more efficient than using a literal. If I use a longer window, so here I'm using a window of 9 characters, which is almost passive-aggressive because if I use a window of 9 characters, I need 4 bits to represent the distance. But if I'm going to use 4 bits, why don't I have a window of 16 characters? Well, it's because I'm trying to prove a point here. And so in this version, where I'm using a window of 9 characters and then allowing lengths of up to 18, so I can go all the way to the end of the buffer if I want to, well, then the distance length pairs require 9 bits apiece. So in this case, it's better to encode literals directly than to encode back references of length 1. So this encoding here, full of back references of length 1, isn't as efficient as just encoding these things as literals like this. So here I'm only generating back references if it's more efficient. And the authors of LZSS actually included that as a constraint. It said that an encoder should never emit a back reference if a literal would be better, whether it is one literal or several. Because you can hopefully see that there are cases where a back reference of length 2 is actually less efficient than 2 literals. If my back references require 32 bits, then of course it's better to generate 3 literals than a 3-character back reference. And it might be a tie for a back reference of length 4. So LZSS had this idea of we'll have back references and literals that you can mix however you want, but the compressor should never generate a back reference unless they actually save space. And that's a constraint that I think I can agree with. Of course, we shouldn't waste space. If we can avoid it, let's not waste space. So generally speaking, if you actually look at the scheme, LZSS should be, logically the ancestor of what deflate uses. What deflate does, which we'll talk about in the next lecture, is basically LZSS. It's LZSS with a couple of small tweaks, a couple of implementation-specific tweaks, but I would argue it's pretty clear to me that it's LZSS. Now, the waters are muddied a bit here because the documentation for deflate refers to what deflate does as LZ77. And you can be the judge of that yourself, but I'll bet that when you see what deflate does, you will agree that it looks very little like LZ77 and a lot like LZSS. I think this has to do with the fact that some people might argue that LZSS is too small of an improvement to get its own name. That is, LZSS is just LZ77 with some tweaks, so we shouldn't even refer to LZSS as a real scheme. I don't buy that because that's going down the road of we should only name things after the most famous people. So Lempel-Ziv are famous, so they get something named after them. But nobody knows who S and S are, so we're not going to call this LZSS. We're going to call it LZ77. That's not a healthy academic practice in my mind. So I believe that deflate is an LZSS-based scheme, and I think you will agree with me once you see what deflate does. Now, this issue of only emitting back references when it's more efficient, so that explicit constraint of we should never emit a back reference unless we save space, that is a bit more complicated than it seems. So if we know that every back reference is 32 bits, and if we know that literals are 9 bits, it's pretty easy to compute how long a back reference has to be before it's going to be actually efficient to use it. However, in a scheme like deflate, one of the things deflate does that muddies the waters there is that in deflate, back references can have different lengths. And it gets sort of worse. So not only can back references have different lengths, the encoding of a back reference can contain a different number of bits depending on how far back the back reference goes and how long the back reference is. So a very large back reference, like go back in time by 30,000 characters and generate 100, will take up more bits in general than a back reference like go back in time by 5 characters and generate 3. But it gets worse. So that's difficult because it means that the encoder now has to figure out not only is this a good back reference, but is this particular back reference, because you have to figure out the size based on the back reference's content, is this back reference more efficient than 100 literals versus is this back reference more efficient than 3? But it gets worse because it turns out that deflate, once you have generated your back references, it goes and runs all of the symbols, including back references, through entropy coding. And that means that a back reference like 5:3 ends up being given some prefix encoding. And as we know, the length of the prefix code is based on how frequently this back reference occurs. That means the number of bits you need for a back reference like 5:3 will vary between different encodings. Depending on what you are encoding, the back reference 5:3 could show up a different number of times, resulting in it having a different encoding length, which results in a pretty intractable problem. So as it mentions here, depending on the properties of the data, it could end up that a back reference like this one requires fewer bits than a back reference like this one, even though that makes very little sense, because it could be that depending on your data, this back reference shows up so many times that it receives a short encoding with prefix coding. And similarly, you could end up with cases where even tiny back references, like back references at like 100:1, so a back reference of length 1, ends up with a shorter encoding than some literals, because we subject it to prefix coding. Okay, now that's something we'll worry about in the next lecture. It's a weird issue, something we'll think about a bit for assignment 2, but it's not so much of a big deal for LZ schemes by themselves. One thing we should consider is, suppose that we give a relatively simple but specific encoding for back references. So I tell you things like the distance is going to be represented in 5 bits and the length is going to be represented in 6 bits. Given a particular back reference, I don't know, like this one, tell me whether or not it's better to just encode this as literals or to encode it as a back reference. So giving you the number of bits, it becomes a pretty simple arithmetic question as opposed to this weird, intractable, sort of nebulous problem of how do I know how long the encoding is going to be if I haven't done the prefix coding yet, that we're going to get at in the next lecture. Now, one other note that I want to make now that we've seen LZSS. So from a practical point of view, the main point of this lecture is to talk about LZSS so that we have it for the next lecture to talk about deflate. There are still about 100 slides left, so we still have stuff to talk about, but most of this is conceptual stuff. One thing we should consider, though, is we've noticed when we talked about delta compression that RLE is a pretty good thing to tack on at the end of a compression pipeline, or somewhere in the middle. We noticed that there are certain things produced by compression schemes that RLE is really good at cleaning up. So the question here is, if I've used a Lempel-Ziv scheme, is it a good idea to throw RLE at it when I'm done? And one issue we observed in the delta compression lecture is if we add RLE on to the end of an existing scheme, so if we take our in the delta compression lecture, we've got our predictive delta compression model, and we just stick RLE on at the end of it. One disadvantage that could incur is that we have all this extra overhead, which is the result of using RLE. So we end up wasting bits on encoding zero-length runs, which can be remedied in a variety of ways. One remedy would be a bzip style scheme where we only encode runs of a certain length or whatever. But there are reasons why bolting on RLE to the end of a pipeline could be a disadvantage. RLE can help a lot in some cases, but it sometimes is a disadvantage to use RLE. And the point I want to make is we don't have to worry about that, because it turns out that RLE, a certain form of RLE, is built in to Lempel-Ziv schemes all the way back to LZ77. And what's so convenient about this is you get the benefits of RLE, but you do no extra work. Whatever logic you're already using, so whatever code you're already writing to take your input sequence and produce back references, will do the necessary RLE step automatically, because it turns out that back references themselves can be used to produce the effect of RLE. And we can see it in this input here. So I've got an input with a bunch of B's in a row. Okay, so I generate the A, I generate the B, and for the sake of this example, we're using LZSS, the LZSS style encoding. And then I see a whole bunch of B's in a row. But what I can do is generate a overlapping back reference. So instead of just generating a bunch of literals, what I can do is observe, well, I'm staring at a sequence of 5 B's in a row. If I go back in time by 1 character and then march ahead by 5, I will generate all 5 of those B characters. So I take this subsequence of 5 B's and just paste it on after AB. So this is one of those overlapping back references. And you can satisfy yourself that you can indeed recover this. If you were given the back reference 1, 5, I've just decoded A, then I decode B, then I've got to decode 5 characters starting here. Okay, well, I decode the first character, it's a B. There's the second character, it's also a B. Okay, there's the third character, it's a B. There's the fourth character, it's a B. And then there's the fifth character, it's a B. So I am able to recover it because the back reference does go back just far enough in time that I'm able to reproduce all the characters. I can still stay 1 step ahead when I'm decompressing. All right, great. That means I don't have to worry about building on an RLE step if I'm using a Lempel-Ziv scheme. And that means that schemes that rely on that have a step that is some LZ scheme, so deflate is one example, as is LZMA, have RLE built in for free. You don't have to do any extra work. It just comes for free with the Lempel-Ziv scheme. When you are working in a compression environment where you don't have an LZ scheme handy, so bzip doesn't use any LZ scheme, then if you want the benefits of RLE, you have to use RLE yourself. And bzip, as I've mentioned before, uses RLE twice, and it gets, I guess, differing benefits both times, but it's able to get some benefits from both RLE stages. And we'll talk about bzip in a later lecture. So now I want to talk a bit about the other members of the family tree. What I want to do at least is get us to the point where we can connect LZW to LZ77, because you've now seen LZ77, and I think you'll agree, it looks quite a bit different from LZW. So where's the missing link? Well, it's this one, LZ78. And I keep mentioning there is this schism in the family. There's this side of the family that likes using symbol tables, and there's this side that likes just generating back references directly, so representing back references explicitly as a pair of numbers. And as I've mentioned, I believe that history has vindicated this side of the family. For the most part, it seems like schemes that represent back references explicitly seem to be better. One other way of viewing the division in the family is between, in a sense, this side of the family, through the use of a symbol table, it is representing a sort of backward-looking model. Whereas this one is representing a sort of forward-looking model. Although arguably there are ways you could call either version forward or backward-looking, because of course back references always go back in time, and you always have a certain number of characters of future input available. But I want to see if I can convince you that I think that the symbol table representation is sort of backward-looking. So Lempel-Ziv's own follow-up. So they actually designed LZ78 themselves. This was their publication. So they created this division, this split in the family. Instead of encoding back references, LZ78 just creates a dictionary of strings. So it creates a symbol table. And then when it wants to emit a back reference, what it does is just goes into the table, finds where that string was stored, and emits that. We sort of know about this because LZW does something very similar. And I think you'll notice that when we get to it, that LZW is about the same level of refinement on LZ78 as LZSS is on LZ77. LZW harnesses a lot of the same logic as LZ78, but does away with unnecessary formalism, unnecessary bulky encodings. So let's take a look at LZ78. This looks pretty familiar. So for LZ78, we need to have a symbol table. There it is. We need to keep track of a working string and the current character. At each step, we're going to augment our working string, and then we're going to have a new working string when we're done. Unlike LZW, in LZ78, the dictionary, the symbol table, is initialized with only one value, which is the empty string at index 0. And like in LZW, we want the invariant that at the beginning of each step, whatever the working string is, will always be something in my symbol table. So at every step, the working string is in my symbol table somewhere. So I'm allowed to have, at some point in my algorithm, a line like, go into the symbol table, get me the index of the working string, and then emit that index. All right, so we start with a symbol table containing nothing. And unlike LZW, we have to build the whole table up from scratch. So at each step, I'm going to go through this pretty quickly because you're familiar with the basic idea because we've seen LZW. At each step, I go grab the current character, I construct an augmented working string. And we ask the question, like with LZW, is this in the table? And the answer is, well, at this point, so before the step started, no. So we put it in the table, we add our augmented working string to the table at the next available index, and then we reset the working string to be empty. If ever we reach a point where the augmented string is not found, the working string is reset to be completely empty. Now contrast that to LZW, where we reset the working string to be only one character long. We don't do that here. We reset the working string to be empty, which guarantees that the working string will be in the table, because we know the empty string is always in the table. And then at each step, we emit a pair consisting of the old working string. So when I get to a step where I have to clear the working string, like this one, I'll use this slide as an example. When I have to clear the working string, I have to print out, I have to emit some output, just like in LZW. The output I emit is a pair. So here we go again with these back reference literal pairs. And the back reference takes the form of the symbol table index of the working string at the beginning of the step. So in this case, index 0, because it's the empty string. And there it is again, a back reference consisting of an empty string. That seems like a waste of space. And then the literal is going to be whatever literal broke the augmented working string. So we added something to the end of the working string, it was no longer in the table, and so we emit that literal. That's the thing that prevented us from having a longer back reference. And that means, just like with LZ77, the first few bits that we output, the first few pairs that get output, are going to be symbol table index 0 followed by a literal. So we have the same essential inefficiency that we had with LZ77. So notice how if we don't find the working string in the table, we emit this pair I, C, where I is the index of the old working string and C is whatever literal we were encountering at this step. So very similar to LZ77, instead of emitting a distance length pair, we are emitting some index from our symbol table. All right, and then at each step, we're adding more things to our symbol table. Unlike LZW, the single character symbols aren't already there, so we have to add them ourselves. And that means that we spend a lot of time just filling in indices of the symbol table with single characters. This could be beneficial because maybe we don't need every single character symbol. This sequence doesn't contain most of the characters on your keyboard. LZW wastes a bunch of symbol table indices on characters that never appear, like Z or W or whatever, whereas LZ78 only adds them if they actually exist. And I would argue that from the point of view of from a theorist's perspective, somebody that is thinking about sequences and trying to avoid making generalizations, this idea makes some amount of sense. Why should I assume that every 1-byte sequence will be needed, and therefore why should I waste symbol table entries on those sequences? Okay, so and then eventually we do have some cases where we find the working string. So here the working string was empty. I try adding the character A to it, and it is found. So here I output nothing. I just cycle my working string back, and at the beginning of the next step, it's going to be the character A. So there it is. I add the character S. Okay, but that's not found. Okay, so I do, like I've done before, I add this to my symbol table, it becomes index 4, and I emit a pair consisting of the index of the old working string, so that's this, index 1, there it is, and then the literal that broke the working string, so S. All right, and then I just keep walking. And I think you know enough about LZW that I think you can follow the logic, so we'll skip ahead a bit here, and we'll notice that as time goes by, we're able to take more and more advantage of things that are already in the table. We'll just keep walking until we get some actual benefits of longer than one character here. So eventually we are able to, at this stage, our working string is semicolon space, because in this string we see semicolon space quite frequently, and so it's not surprising that it's going to show up in our symbol table. So there it is. We try adding the character A to it, and in this case, that is not found, and so semicolon space is emitted as this pair here. So semicolon space is index 10, that becomes the first index of the pair. The literal that broke it becomes the second index of the pair. And what I hope you'll notice about this is here, at this step, when I'm encoding at this position, I go looking for semicolon space A, and that's not in the table. So I don't get to emit this as what would amount to a 3-character back reference. Although if you stare at the input, semicolon space A has occurred 2 other times. In LZ77, with a long enough window, I could just go back and say, give me semicolon space A. But in this example, I can't, because the way LZ78 works requires the thing to already be in the table. And when I first encountered semicolon space A, that's the step I put the semicolon in the table. That's when I generated symbol 6. And obviously, I'm not allowed to add a symbol to the table. Given the rules that I'm using, when I add a new symbol to the table, it'll always be a previous symbol plus 1 character. So I'm not allowed to add semicolon space A all at once. Instead, the first time I see it, I add the semicolon. That's going to be index 6. The second time I see it, I add semicolon space. That's going to be index 10. The third time I see it, that's when I generate this pair here. I use the symbol at index 10, and then I add an A to it, and then I add semicolon space A down here. So all things considered, this does seem to be a little bit less efficient in some ways than LZ77. In exchange, I get the, streamlined effect of having just these indices as opposed to explicit back references. Okay, so we'll finish encoding, and in any event, we are able to get a few cases where back references refer to a 2-character symbol followed by a literal. And so LZ78 is pretty similar to LZW. It's more bulky because we were requiring things to be pairs, so we require back reference literal alternation, although again, back references are indices into a symbol table. That means that we end up with a bunch of these pairs that contain this 0 back reference that just wastes space because it's an empty back reference, so I'm spending bits telling the decompressor to do nothing. In LZW, the way that this problem is remedied is by observing that these 0-character back references correspond to just emitting a single character, a single 1-byte literal. So by adding all single bytes to the symbol table in advance, LZW skips this step. It also is able to, of course, avoid having this forced back reference literal alternation that seems to be a little bit inefficient as well. In this case, these slides are actually stepping through the example I already did, so I'm going to just skip over this. So the approach that LZW uses, I think, is pretty much the same improvement that LZSS made on LZ77. Instead of forcing there to be pairs, back reference literal, I allow a symbol. I have everything in my table, so I have any alternation of back references and literals that I want. I can have a back reference, then a literal, then a back reference. LZW does one more clever thing that LZSS doesn't. So LZSS requires there to be a distinction between is the next thing a back reference or is the next thing a literal. With LZW, we can achieve the effect of having any combination of back references or literals, but actually in LZW, everything is just a symbol index. There's no such thing as a back reference or literal. There's just an index into the table. Literals are represented by indices that are small numbers, indices that are less than or equal to 255. Back references are represented by indices that are greater than 255. That's it. So LZW is actually more streamlined than LZSS. I would still prefer LZSS. I think LZSS is a better scheme for a lot of different reasons. One issue here is that although it's not obvious, the sliding window, in a sense, manifests in the form of how long the symbol table gets. The problem is, unlike LZSS and LZ77, where it's very easy for something to just exit the sliding window, that is, the window can truly slide. In LZW and LZ78, the only real way of flushing out the window is by clearing the symbol table. or by adopting an approach where indices work on a rolling basis. That is, as you go further and further into your input, old indices get cleared automatically. That does not seem very convenient, it doesn't seem very efficient, and it doesn't seem very easy to verify that that would result in good behavior. And that's one of the reasons why I think that LZ78 and LZW, why I'm not too surprised that that branch of the family didn't end up winning in the grand scheme of things. And like I mentioned before, in lecture 3 and earlier in this lecture, this idea of using a symbol table is sort of weird because it results in us having to save up symbols for the future even though we don't necessarily need them. I add something to the symbol table because I hope that later I'm going to use that symbol. So that is to say, I'm going to add index 4 to my symbol table, and I just hope that later I'm going to need AS, because if I don't, I've wasted an entry of my symbol table, and that's more bandwidth because the larger my symbol table gets, the more bits I have to send to the decompressor. So I add entries to my table whether or not I end up actually using them, because I don't know whether I'm going to use them. When I'm standing at this point in the sequence, encoding this character S, all I really know about is what's in my table right now and the current character. All I can do is look backwards. And so I add stuff to the table because I can't see in front of me. There's a dense fog in front of me. I don't know what I'm going to need later, so I have to add everything I might possibly need later to the table based on a backward-looking view of the world. I don't really have the same look ahead that I have in LZ77. There is still certainly a sense of look ahead because you could argue that the working string as I build up a symbol is just picking up future characters and using them, but I don't think it's in the same obvious way it exists in LZ77 and LZSS. Whereas in LZ77 and LZSS, I'm allowed to stand at this point, look into the future, and decide whether I can pull something out of the past that helps me out, as opposed to the much more bumbling approach of LZ78 and LZW, which is basically just add everything you've ever seen to the table and hope that I need a bunch of it later in the future. Because if I don't, I've wasted a lot of bandwidth and time, frankly. So eventually we're going to want to implement deflate. Now we're actually, at this point in the course, we're done with this branch of the family tree. I wanted to talk about LZ78 so that you could make the connection between LZ77 and LZW. And you can see it's there, but quite a bit changed in LZ78. And quite a bit changed in LZW. LZ78 by itself is just like LZ77, a bit too theoretical, a bit too conceptual. It's good for proving a point, but as far as getting real compression, the insights of Welch in LZW were pretty important to streamline the scheme. And for what it's worth, the streamlining in LZW, I think, is a bit more intense than the streamlining in LZSS, because in LZW, there's only one type of symbol. It's just a symbol table index. Whereas in LZSS, there has to be some way of distinguishing a literal character like A from a back reference like 3:2. So LZSS is certainly more streamlined than LZ77, but not nearly as much as LZW. Whatever, that said, I like LZSS better. And I think modern LZ schemes tend to be descendants of LZSS. So for example, LZMA is also a descendant of LZSS. Whether or not people think that is a different question. So as I said, there seems to be a bias towards thinking that every scheme that uses explicit back references is just a variant of LZ77, and I think that's not fair. I think S and S deserve some credit for the streamlining that they did in LZSS. So deflate, which we'll talk about in the next lecture, fundamentally deflate is the combination of LZSS followed by a prefix code, but of course you'll use Huffman coding for that. We'll notice that most of the complexity of deflate isn't in LZSS or Huffman coding. It is in how do I take a sequence of symbols that comes out of LZSS and then somehow make a Huffman code for those symbols, keeping in mind that the symbols could be the letter A, but also could be back references. How do I make a Huffman code over those? And then the real problem, how do I tell the decompressor what I did? How do I tell the decompressor what Huffman code I am using and what back references I have in such a way that the decompressor can both recover the data and I don't waste a whole ton of space doing so? That's a big problem. And deflate solves it in an extremely complicated, layered, and intricate way. I almost think about deflate as being a very intricately designed analog watch or something. It's a whole bunch of tiny, precision manufactured gears that fit together perfectly to produce compression. And so the slide, which is a bit more cynical, I guess, calls these things bizarre meta compression tricks. Okay, fair enough. I guess that's also a valid description. So we'll talk about those bizarre meta-compression tricks at great length in the next lecture. In the meantime, I want to skim over the subject of how do I actually evaluate the LZSS algorithm. So we get the idea. I want to go through my input stream and find back references. How do I do that? If I have a large sliding window, if I'm looking at this character, the letter A here, and I know the next character is B, followed by a C, followed by another C, but I've got 30,000 characters of history to evaluate to find a back reference, how can I do that quickly? I want to do that test. Is there a good back reference? I want to do that test for every single character of input. And the window for deflate is not a big number by modern standards. 32K, not a big number. For LZMA, it could be gigabytes. So of course, I need some fast way of doing that. So for the sake of formalizing it, and what I'm going to do in the next few slides is just skimming over some ideas. So I'm not going to write any proofs. I'm not even going to do any full implementations. I just want to skim over a few different ideas. For the sake of doing that, we should formalize what I'm talking about. So let's represent our entire window, history and future, as one long sequence, where the indexing changes at each step, but at every step, we'll say C0 is the current character, C1 through CK are future characters, and C-1 back to C-N are past characters. What I want is to look at this and to find, if such a thing exists, a pair Q, L, so a back reference of distance or some previous index followed by a length that gives me, I guess, the longest sequence that matches the future characters. So I want the longest possible back reference. Now it turns out that searching for back references can be a bit more complicated than that, because it could turn out that if you've got a back reference of length 5 that goes back in time by 100, and you've got a back reference of length 3 that goes back in time by 10, in many cases, this back reference will be way easier to encode. It'll require way fewer bits. That means it might actually be better to encode this back reference than this one. And there are other very weird situations that could occur. So for example, what if it's equally space costly to encode both of these? So what if it costs the same amount to encode any back reference? There are still cases where you would rather encode a back reference of length 3. So one example would be, you could encode a back reference of length 5, and then maybe when you're done, the best you could do is encode a couple of literals or a short back reference or something. But on the other hand, if you were to encode a back reference that was shorter, you could benefit from then encoding a long back reference afterwards. So I could encode a back reference of length 3, followed by a very long back reference, I don't know, go back 600 characters, and then encode a back reference of length 10 or something. There are lots of weird issues that occur. So first off, we have something to formalize the idea for searching for back references. But one thing we have to keep in mind absolutely is that nothing in the requirements of an LZ scheme requires that you generate any back references at all. A back reference is a means to an end. It's a way of saving space. There is no requirement that your LZ scheme generate the best back reference at every step or even any back reference at every step. And that means, as far as solving the problem for how to find back references, you just want a good back reference, if you can find one. You want to spend a reasonable amount of time looking for a good back reference and then maybe give up. You don't want to waste a huge amount of time searching for a back reference if the best you can come up with is a back reference of length 1. And you also don't need to worry too much if, you find a good back reference, but maybe there's a better one out there. Maybe it's not worth wasting too much time searching for a better one if you already have a pretty good one. So obviously we do want to find the best back references that we can, because the better we find back references, the better compression we're going to get. On the other hand, there's no requirement that we come up with, I don't know, an optimal back reference in every case. And you will discover, and real schemes also do this, you will discover that finding a good back reference and then giving up in the interest of saving time and moving on can be quite helpful. And deflate encoders do that all the time. In fact, recommendations in the deflate specifications for how to find back references are basically full of encouragement to only look for good ones. Don't worry about finding the best one, because the data structures that are recommended in the documentation don't really allow you to always find the best one. They just allow you to find a good one and then move on. Okay, one option, use linear search. This is, frankly, if you're writing an LZ scheme, do this one first. So, of course, if you want to find the best back reference, the best, you could just iterate through every single previous character, all of them, even if that takes a long time. You could do that, and you would eventually find every possible back reference, and you could choose the best from those. That's not great because it scales linearly, and we are performing this operation on every single input symbol. So every piece of our input sequence, so again, let's look at an input sequence here. So here's my input. I'm going to stand at this character and find a back reference. If I can't find one, then I generate a literal and move on. If I can find one, maybe I skip over a few characters. But every time I'm looking at a piece of input, I have to search for back references. So linear search over a large window will become pretty costly very quickly, especially if I have a big sliding window. So it's simple. That's one benefit. One benefit is that it's simple. One benefit is that you can write it quickly and verify it very easily. But maybe there are things we can do that can save us some work. Because it's true that I can't benefit from a lot of traditional data structures easily here because, as we know, if this is my current character, then I can go searching for back references among previous characters. But because the window changes at each step, a traditional search-based data structure wouldn't help me without a bunch of, a bunch of tweaks. If I find some way of saving the work, because if my window is really long, and I've got, let's say here's the beginning of my window, distant in the past. If my window is really long, then the window I'm searching for the sake of this character is this stuff. The window I'm going to end up searching for this character is this stuff. So a lot of it is exactly the same. So it would be nice if I had some way of preserving some of the work that I do between steps. So first thing, don't be a hero. When you're doing assignment 2 and you want an LZ scheme, you want LZSS, use linear search. I'm serious. If you get linear search to work and you discover that it's slow, then work on making it faster. It's way easier to improve working code than to write broken code and just hope that you can make it work in time. Starting in with a complicated data structure will result in tons and tons of frustration unless you just happen to be very, very lucky. If there ever were a time not to push your luck, it is on this assignment. So don't be a hero, just use linear search, then make it faster if it's too slow. So one other option we could try, or I guess a category of options, would be to consider our entire history. So our entire history is some long window of previous characters. What I could do is consider this really, although it is one long string, I could treat it like a whole bunch of short strings. I could treat it like a long string starting at character -n, a slightly shorter string starting at character -n-1, all the way down to a very short string beginning at the character one character in the past. And then I could sort of pretend, although it is just one big string, I could pretend that I'm working with a large collection of strings. And then put all of those strings in some data structure with the understanding that at each step as I move along, I'll delete the oldest string because it'll age out. It'll exit the sliding window. But notice how all of the other strings are still in there. So maybe whatever benefits the data structure carries, I can preserve them. I can save work between steps. And then at the end of each step, after I've removed old strings, I'm going to add new strings to my sliding window. Because at the end of my step, where I've encoded character C0 is going to move into the past at the next iteration. And so I want to add that substring to my data structure so I can search it for finding future back references. So one option I could use here if I do this, and this doesn't have to be done explicitly, because obviously if I have 32,000 characters here, I don't know that I want to generate 32,000 independent explicit strings. That's going to be a lot of space. Not that much. I mean, I could store all of that in memory, but it is quite a bit. Remember that I'm doing this notionally. I'm thinking of my single 32,000 character string as a bunch of individual strings. I don't have to actually store those strings separately. I could use some clever, so in C, for example, I could use some clever pointer shenanigans. I have a variety of clever tricks I could use to pretend that I have 32,000 different strings, well, actually deep down only using one array to represent all of them together. They can all share the same array. So I could try this trick where I pretend I impersonate this bank of strings and then enter them all into a data structure like a binary search tree. So I could try it like this. I would want a self-balancing binary search tree, ideally, because otherwise I could get bad worst-case performance, to the point where it would actually affect me practically. So if I'm using C++, as many of you are probably going to do on the assignment, and I want a binary search tree, well, they're built in. Map and set are balanced binary search trees. I'd have to do a little bit of fiddling around because I wouldn't be able to use functions like find. I'd have to use functions like lower bound or something similar for reasons that'll become clear in the next few slides. What I could do is enter my entire history, all of the substrings of my sliding window, into a binary search tree, as long as I've got some mechanism for finding when I want to delete the oldest string. So at the end of each step, there's going to be one thing I have to delete from my data structure to keep the data structure at a reasonable size. As long as I have some logic for finding that string and then removing it, which there are functions to support that in log n time, then I could use a binary search tree. I wouldn't be able to use the find operation because the back references I'm searching for are unlikely to be exact matches. So for example, if I am currently looking for the text, I'm not going to use, let's do, if I'm looking for the text WXYZ, and there is somewhere in my buffer a previous string that begins with WXYABC. Well, if I go searching for WXYZ, I'm not going to find this because this is different. And in a binary search tree, the find function is designed to return an exact match. What I want is to figure out where in the tree do strings beginning with WXY live. And then if I have a particular string, I can go looking around and decide if any of the nearby things are what I want. So if you can get me to a certain neighborhood, I can wander around that neighborhood using an iterator of some kind, so performing an in-order traversal, which can be done relatively quickly. I can wander around that neighborhood looking for good matches. So what I basically want to do is search for I don't want to do a find operation, I want to search for the insertion position. So if I have the string WXYZ, the insertion position, if I try and actually do a find operation, I go, okay, right, and then right, I guess I'd end up here. This is where WXYZ would go. I don't actually want to insert it. What I want to do is figure out where I would insert it and then wander around nearby, look at the neighboring nodes to see if any of them represents a good back reference. In this case, it turns out that it doesn't. So for example, in this tree here, suppose that we've got A, B, C, D in our look-ahead buffer. Now notice that I don't actually have A, B, C anywhere in the tree. But suppose I want a back reference that would help me with A, B, C, D. Well, none of the entries of this tree do that, but I could go looking for where I would insert A, B, C, D. So the insertion point would be somewhere around here. I guess it would be, if I inserted it, it would go there. So A, B, C, D would end up here. But what I do is I search for the insertion point. There are a few ways to do that. If you were to use the std map object or std set, you could use a function like lower bound, which is like the find operation, or you could use upper bound. It's like the find operation, but if it can't find the thing you're looking for, it returns an iterator to the nearest part of the tree that does represent something close. So basically, it does sort of localize you to around the insertion point. So what I do is I find where my current string, A, B, C, D, I figure out where it would go. And then I look around that neighborhood. So if I have an iterator, I just sort of walk around. I look at this, say, well, that's a decent back reference. I could also do, if I back the iterator up by 1, I would get this, which is the previous node in an in-order traversal. I could walk forward and look at this. I could just wander the neighborhood, and the tree does do, I think, a lot of the work of eliminating most of the possibilities. So I'm no longer doing linear search. I've usually eliminated most of the possibilities, and I can decide how much of the neighborhood I'm going to wander around before I give up. I could wander a little bit and say, oh, I found a good back reference, or I can't find anything close, so I'm going to give up. I mean, if I see ACC, I know that I'm going any further than ACC won't help me, because once I've hit ACC, the next stuff in a traversal will be even further away from ABCD. So the idea here is using a binary search tree in a sort of unconventional way, but a way that it can be adapted to work with pretty easily, such that I can then localize my back references a bit better. So anything's better than linear search, and if I can eliminate enough possibilities, because I'm only looking for practical performance, not some asymptotic guarantee, I just want a data structure that results in fast code. I don't care that much whether there is some theoretical worst case, because I could set some reasonable limits, like never look at a neighborhood of more than 10 things, or something like that. And so the slide, I think I've talked ahead of the slide, so I'm going to skip over. One other option, which is in the same vein, is to try and adapt some other existing data structure that we know a lot about. So the other option, if we think about searching with binary search trees, we think back to our first year courses. What else do we use for searching quickly for stuff? Well, we could try a hash table. I could come up with a clever hashing scheme that allows me to locate back references quickly. And the reference encoder and decoder for deflate do this. They actually include recommendations for a good hashing scheme to use. And those recommendations are essentially amount to, here's a good hashing scheme, it's pretty fast, it's not going to find the best back reference in many cases, but it's going to be fast enough and find decent ones most of the time. And the deflate encoder you likely would use in practice, so the one built into most people's operating systems these days, the one that comes with their OS, probably does that too. It may not find the best back reference, but it's really nice and fast, and it does a pretty good job. So the problem is that a hash table, just like a binary search tree, but even more so really, is designed for exact matches. A binary search tree has this property of keeping all the keys ordered, which means that even if you can't find an exact match, you sort of know where things are. And if you look at things nearby where the match would have been, you can find things that are similar. A hash table usually is designed with the opposite goal. So those of you, I guess you all know about hash tables. You should know a decent amount about them. As you know, most of the time, the hallmark of a good hash table is that if you take two similar things, so ABC and ABD, and you have your hash table, a good hashing scheme, on average, should spread those things out pretty far in the hash table. I don't want any clustering, especially of related keys. I would like to throw a bunch of related keys into the hash function, and I want them to be spread out as far as possible. So we usually design our hashing scheme to spread elements out evenly, but the criteria we're using here sort of requires the opposite. What I want is for similar strings to be sort of close together or to be easy to find, because I'm not expecting when I go looking for a back reference for it to be the exact thing I'm looking for. I might want a back reference for, I don't know, ABZ, and I would want to know that ABC and ABD are available, even though of course ABZ is not an exact match. So one option, and I'm generalizing a bit here, but come and talk to me in the office hours if you want to try this out. One option is just to design a bad hash function, basically. I'm just saying here to sabotage the hashing scheme. That's a sort of a judgmental way of putting it, but it's I guess relative to what you're used to as far as designing a good hash function. Usually we think of a good hash function for the sake of a hash table as one that tries to differentiate any elements, even keys that are similar. I want the opposite. So I'm going to design a deliberately bad hash function. One example is in a context of something like deflate. So we'll see next time that in the deflate scheme, you're actually not allowed to generate back references of length 2 or 1. The scheme doesn't support them. Every back reference must have length 3. So suppose that I care about finding back references of length at least 3. And I think in general, it's reasonable to assume that the longer I'm looking for, so if I have this sequence of look ahead, it's far more likely that I find a back reference of length 3 than a back reference of length 4. And that's because every back reference of length 4 is also a back reference of length 3. So in general, as the length increases, the probability that I'll find a back reference of that length will decrease in general. There are weird cases, so I mean cases where every character in the file is the same, where maybe that doesn't happen. The probability of any length is basically equal once you get going. But in general, the longer the back reference is, the less likely it is I'm going to find one. So what I could do is I could design a hash function that only looks at the first 3 characters of the string. So ABCDE and ABCXY and ABCYZ. The hash function only looks at the first 3 characters, so all 3 of these things will go to the same entry of my hash table. So if I have a hash table and I use that deliberately bad hash function, only looks at the first 3 characters, all of the strings beginning with the same 3 characters go to the same entry of the hash table. Whereas, for example, if I have strings beginning with a different 3 characters, the hash function, if all goes well, would send them somewhere else. So what I want is a good hash function, but I want the hash function to only look at certain parts of the string. So it's good in the sense of, for the parts of the string it looks at, it spreads things out pretty well. But it's bad in the sense of it only looks at part of the string, which is what I want. I want strings beginning with the same first 3 characters to be put in the same place. And then once I get there, so I could use a hash table with chaining or something. So I could have a hash table where once I get inside of an index, I just have a linked list sticking out that contains every string beginning with those 3 characters. And maybe I set a maximum length or something on that list to make sure that I don't have any weird pathological cases. So once I get into the bucket corresponding to the first 3 characters being ABC, I have all of the back references beginning with ABC lined up and ready to go, and I can look at them. I could basically then use linear search or some other data structure or whatever. I could then look at them and decide which back reference I want. And that's a way of getting sort of the best of both worlds. I still get linear search, that is, I don't have to do too many complicated things once I'm inside of a bucket of the table, but I am able to spread out my different back references a bit. So once I'm in a particular bucket of the table, I'm guaranteed to have at least some back reference available. Even if I run out of energy and I decide to give up after, let's say, looking at, I don't know, 3 or 5 or 10 elements, I will at least have a back reference when I'm done. And also, if you consider the number of possible three-character symbol sequences isn't very many, I could make a hash table big enough for there to be one entry for every possible three-character prefix without running out of memory, which would mean that I don't have to worry about collisions in the traditional sense of a collision between two distinct prefixes. So that's one other option. And I think for many of you, you'd probably rather write a hash table than your own binary search tree. And I guess re-instrumenting the built-in C++ binary search tree is also a bit of an acquired taste. So I suspect that those of you that want a fast data structure might want to try this one first. Now, there are other requirements we should think about, and I'll talk about this a bit more when we see them, but I guess overall, if I want to design some clever data structure to find back references quickly, what I need is the ability to add new characters to the history easily. I also need some way of expunging old stuff. So if I am walking through my data sequence and my sliding window, so suppose in this case I have a sliding window that's 3 characters of history. Well, that means that by the time that when I encode the D, my history is ABC, but as soon as I'm done with the D, this substring, ABCD, has to be removed. I have to delete this from my history because the A is no longer available, because once I hit the E, my sliding window of size 3 doesn't, like the A has gotten stale, it is aged out of the sliding window. If I'm designing a clever data structure, I need some way of doing that quickly, of both finding the substring beginning with that character that's about to disappear and removing it from the data structure. Now, with the hash table, what I would do is just do a lookup, go into the bucket, and then delete that element of the list. But I have to do that myself. Otherwise, the table grows without bound, because as I compress more and more data, more substrings end up clogging up this data structure, even though I can never use them. If I didn't remove the ABCD from the table, from my data structure, maybe it's harmless, it's fine if it's still in there, but I'm going to have to keep looking at it, I'm going to have to waste time looking at it, and of course, if I'm way later in my sequence, if I'm down here, if I still have access to this ABCD, that's one thing, but I can never generate a back reference going back that far. If my sliding window has size 3, the decompressor will not accept a back reference to anything earlier, so I need some way of removing stale data. And of course, I have to have some way to keep memory consumption under control. And part of that comes down to implementing these two things efficiently. I need some way of adding stuff in a relatively clean way, in a way that doesn't eat up too much extra space. I need some way of deleting old stuff efficiently. So not only being able to go in there and find it, but also delete it quickly, and also in a way that doesn't leak memory or whatever, so that as time goes by, if my window is small but my file is large, I can still keep my data structure up to date without wasting huge amounts of space. But all of that is implementation specific stuff, so come and talk to me about that. We'll talk more about that as we approach the due date of assignment 2. However, I will observe we now know about LZSS, we know about prefix coding, and so we are finally prepared to start our ascent and climb the mountain that is the deflate scheme. And that will be the subject of our next lecture.